All right. Okay. Hey, at the end, good to see you again. Cool. Yeah. I'll give it another minute and a bit before we kick off. Just let people roll in. It's a rainy Sunday afternoon, and well, I was gonna say sunny Saskatoon, but I guess not so much. Rainy Saskatoon. Today we are writing some profunctor optics. Gonna make myself coffee here. Oh yeah, there we go. Steaming hot cup of joe. Hey Tom, good to see you. I could do with some popcorn right now, actually. Get the extra buttery stuff right from the theater. Oh yeah, I guess how I'm trying some new streaming settings today. Hopefully, people can kind of read my screen here. Is this approximate? Here, I'll just do like, let's throw the MIT license up on there. Can everybody read this okay? Should have 1080p, I think. If you don't, then let me know if you can't read this at all. I can always upsize the text or whatever. Just want to make sure everybody can see what's going on. Cool. All right, let's get started. So, it's always weird not having music for this sort of thing. It's a little small. Okay, we'll go up a tick or two, but it should be a lot better than last time where I just wasn't streaming with enough resolution. Yeah, okay, we'll go up, but half the laptop screen is not. Okay. All right. Well, that might be too big. Let's try and find a happy medium here. Okay, so what we're gonna do is we are writing some profunctor optics today. So what are profunctor optics? I guess would be a great place to start. Hopefully, if you're here, you have a rough idea of what optics are. So when I say optics, I mean lenses and prisms and isos and traversals and all of that good stuff. But what do I mean when I say profunctor optics? So you might hear these words like kind of thrown around a bunch. The alternative currently, there are a bunch of different alternatives. There's, probably 3 or 4 different optics encodings out there. There's like concrete optics. I don't know if that's like the term everybody's using. They're not very common these days, but you can actually encode optics as just records of functions, but it doesn't really scale very well. But what Haskell primarily uses, so for instance, the lens library, here I'll actually, let's pull open the page and we can show off what the, what the other options are. All right, let's full screen this sucker. So we'll go into lens. Can you guys read this font okay? I can always bump this up a little bit too. But when we talk about Van Laerhoven lenses, which is what the lens library uses, we can see basically a Van Laerhoven lens is anything that, I'll pull up the, here we go. Where did it go? Here we go. So anything that kind of matches this signature here. So it has a function on the left and it will run some alterations on it to end up with a function that looks like this. And you can tell something's Van Laerhoven if it goes from an A to an f of b. This f is where all the magic happens. Okay? So profunctor optics look a little different. I wonder if I can, here, let's pull up the pure script profunctor lenses, sure. Okay, so this is one of the main pure script optics implementations. I'm going to try and pull it up here. I don't go digging in here a whole lot, but if you're looking for profunctor optics, this is a really good implementation. This is basically the canonical implementation. So how is this different? Well, if you look at, for instance, a traversal here, we can see the type signature of a traversal. It has some constraints on P, whereas the lens implementation has constraints on F. Got applicative. And what is an optic here? So an optic in its simplest form takes some P, there's actually no base requirements on it, and it turns it into some other P. So this is literally just a function on some data structure P with some parameters. We don't know anything about it, and we change it into some other one. Okay, this is very, very, very general. But what we can do is we can kind of compare the two. So here I'll open up a scratch pad or something. Let's just open up our, whoops, do I not? Oh, I don't have anything in here. I'm going to, we're going to remake this. Let's make a new project here. So I'm going to say make a new project. Good. Proton. All right. So I've just got my basic Haskell project structure here using stack. And I'm just going to open up, it always starts you off with this little lib function here. Oh, it's doing the same thing as before. Okay, I'm just going to change my LTS here to, let's do 14.22, I think I have installed everything. Let's try to stack build. Brilliant. The big thing is I like to have intro so that I can use my editor nicely. Okay, this looks happier. So we'll just clear out all the basic stuff here. I don't actually need an executable, so this will just return unit. Okay, not important. So when we talk about these kind of optics, we can see that a traversal in Van Laarhoven, or just any optic really, looks A to F of B to S to F of T. Okay, so, whoops, what am I doing? There we go. And in profunctor land, it goes PAB to PST. So you can actually see this one's already a little simpler, I guess. But we have less information about what's going on. But we can actually see this is a specialization, or sorry, a generalization over this. So if we pick P to be something like the function constructor, we can end up with something like this. So I'll do weird brackets here. Feel free to ask questions in the stream, of course. Teaching, so we want to make sure everybody can keep up. So we can see actually this kind of arrow, it is a type constructor. It's a type constructor for functions, and it takes 2 arguments, right? It takes, in any given function, it takes the thing that you're passing in, and then you get the thing that you're passing out, that you're returning. And so we can just say P equals this thing, and we kind of can relate the two. I'm getting ahead of myself though. Let's talk about profunctors. So what is a profunctor? This is going to be important. So I think I can just probably write out what is a profunctor. Well, it's a type class. Okay, so it's a family of functors. Yeah, you want multi-parameter type classes. Okay, here we go. So I'm going to name this profunctor prime here. And it is a type of functor that takes 2 arguments. And the way this works, with normal functors, right, you can F-map over them. Profunctor, it still has kind of the idea of F-mapping, but its main operation is something called die map. And, oh, I need a P. That's what I need. Okay. Is this big enough now? Just, I'm getting paranoid. Okay, so die map says that we can take we pass in 2 functions. I'm gonna make sure I get these in the right order. I'll double check. But one of the functions is a contra map, and the other one is a mapping function, which means one of these functions is gonna look a little kind of backwards, I guess. So we're going to say we can go from A prime to, oh, sorry, A prime to A, yeah. And if we go from B to B prime, then we can map a PAB to a PA prime B prime. Now let's see if I actually got that right. We'll check here. So if I do info, oh, I'll need to import profunctors. So data.profunctor, which I think I will need to install. That's right. Okay, it's hidden. Of course it's hidden. So like always, install. We can just add profunctors. So this is one thing, actually, I'll bring this up. This is one of the reasons that Van Laarhoven, oh, and the A and B shouldn't be in the class. You're absolutely right. Okay, it's been a while. It's been a while. I haven't written Haskell in a while. Thanks. We're going to get there. So profunctors is a Haskell library, but it is not inside base. So this is one of the main reasons that Haskell kind of picked a Van Laarhoven representation. Part of it is just we were discovering how to encode these things, and the profunctor implementation wasn't discovered until later. But one of the reasons that we haven't, all migrated is that you do need an extra dependency in order to define profunctor optics. So Van Laarhoven you can define almost entirely with just base until you get into some of the more complex ones, so like ISOs and prisms and stuff. Whereas profunctor optics, we do need this dependency. So I'm going to just restart intro here so it picks up my new library. Should pull in, and now we should be able to import profunctor, and we should be able to get info on profunctor. Great. So you can see class profunctor has one type parameter here. And we've got, so they actually define it, they have LMAP and RMAP, but you really only need to define, yeah, we can see here, either DIMAP or LMAP and RMAP, because they kind of, LMAP is just half of DIMAP, RMAP is the other half, and DIMAP does both. So I usually define it in terms of DIMAP, but that's up to you. And we can see here, if we have a PBC, LMAP will go from, takes an A to a B, and we can see it goes from PBC to PAC. So this is going to look different if you're used to like functor mapping. It looks backwards, right? You think, oh, if I have an A, if I have a B and I want to turn it into something, I would need like a B to something. But what we're actually saying here is, okay, P accepts a B, all right? So if this is a function, we can think of this as like precomposing. So if we have a function A to B, and we want to compose it with a function that's, X to A, okay? Well, if we put this function before this one, so let's say this is F, this is G, don't really need these, okay. Then if we do F after G, then we can see, even though this maps an X to an A, if we run it in this way, it'll actually work the opposite way around. So we go, now instead of an A to a B, now we'll have an X to a B, I believe. Let's just make sure that type checks here. All right. So we can think of profunctors as their first argument being basically they accept something, and their latter argument as they return something. So functions are basically the simplest profunctor. They're the one that are easiest to understand because we work with them a lot, right? So what are we all getting at? Okay, well, let's just start building some stuff. Profunctor, we're not going to understand profunctors in a quick little explanation like this, especially since I haven't really planned the way that I'm presenting it. So sorry, that was probably a little tough to get to. But it'll be more clear as we actually, write some of this stuff out. So I'm going to just comment this out because I'm actually, you know what? Let's maybe use our own profunctor implementation here. So let's write our first optic. So basically, there are so many different types of optics. The easiest one to write in profunctor land is actually setters and like kind of over, and that's because they use this the function profunctor to do their work. So if we're going to describe a setter, we can do a type alias here. So all of our optics are going to be STAB. That stands for, well, I mean, it doesn't really matter what they stand for, but I like to say that the S and the T are structures, and the A and the B are the focuses of the optic. So a setter, now, just like in Van Laerhoven land, all of these optics are going to be existentially quantified over the P. Now what that means is they can, basically, a setter is any function from, for all P, there we go, from P of A to B to P to S of T, where we have some constraint on P, all right? Now this constraint on P is going to change for every different type of optic. Okay, now this is going to bug me that I need probably what, rank n types. Yeah, okay, now it's happy. Okay, so we need to figure out what to put in this slot here for a setter. 1 second. And the reason we need to kind of figure that out is because we want this to work with, you know, effectively any optic implementation, any concrete profunctor. And the reason we want to do that is so that we can compose setters with other types of optics that do more complex things. We basically just need to, you know, keep this as general as possible. So one thing we can do when, you know, you're just trying to build this and you don't really know where to get started, you can always just cheat and, like, you know, look up, oh, look, we've got a setter. Let's see what the type alias is, and it should have a type setter. And we can go in here and we can see, oh, okay, a setter. Well, it just assumes that it's a concrete function, right? So it says, okay, it can basically work on anything that is literally a function. So in our case, what that applies to, you know, we could abstract over the ability to, you know, apply something or whatever, but it's definitely easiest to just say, okay, setters, anything that is literally this profunctor here. So I can do it in this weird kind of prefix notation, and that is valid Haskell, but it's of course much more readable to do it this way. Great. Okay, so this looks kind of dumb so far, but it is correct. And what this says is a setter is anything that can take a function from some focus A to some, you know, new focus type B, and it can run it on an S to get a T. So which sort of actions can we run on setters? So now we need to just actually use this thing somehow. Okay, so the simplest action is called over, and over takes a setter and it takes a function to run on the focus, and then it will run that on this, and it will return the T. So this, some of you might already be noticing, well, if a setter takes an A to a B and returns an S to a T, and that's exactly what over does, what do we put in here? Well, I mean, I think that's valid. Yeah. Or I can just say, well, you know, if a setter is something that takes this and returns that, then we have our setter, and we have our function, and we can call setter on the function, right? Or, of course, we can, you know, basically say over equals $. There's a whole bunch of different ways that we can define this. But really interesting thing is that profunctor optics, if you have the basic optic, you can apply it as you can just literally apply it to an optic and a function, and you have it'll work. So let's actually try this out. So we need to first write a setter, a valid setter, and a setter has this type signature. So let's write the standard. You know, let's focus the first element of a tuple, and we'll make this optic here. So this will be a setter. I'm going to use the expanded version just because it'll be easier to see. And instead of going from an A to a B and an S to a T, we're going to change our structure here. So what is our structure now? Well, our structure is going to be an A and I guess maybe I'll call it first and second. This is going to focus the first and go to first prime. And what do we get out after we've run first to first prime? Well, we're going to get updated. So the updated version, so it's going to be first prime and second. Okay. So what this whole thing does is it just says, okay, well, _1, it takes a function which runs on the first element of a tuple, and then it runs it on the first element of the tuple. So there's a ton of different implementations for this. Simplest one, I'm just going to take an F. I'm just going to pattern match, right? So we got an A and a B, and we'll just run F on the A and get a B. Okay. So of course, we're eventually going to make _1, so the first lens more general. We're going to turn it into an actual lens, but we're going to start off with just a setter. Okay, so now we've got over and we've got _1. We can actually start to use that. So here I can do what is it? Okay, I'm going to set the prompt if I can figure this out again. Set prompt. Yeah. There we go. Okay. I gotta set. You know what? I'm gonna set that in my .ghci because I always forget to do this. There we go. Done. So now we can say over first, and what do we want to do? Well, let's say we're gonna not something, and we're gonna start with false and Bob. Now what do we expect this to do? Well, we expect it to focus the first thing in our tuple and then run not on it, and it works. So this is we've got a setter. It's not really that hard. The wiring to it looks complicated, and we haven't even really mentioned profunctors yet. We're going to do that as we generalize how this works. Okay, so as we add more stuff, more capacity to the first selector, then we'll figure out how the profunctor wires in. All right. So next we're going to write set. So interestingly, set is easiest to implement in terms of over. So if we've already got something which focuses something and runs this function over the focus, well, we don't need to redo that wiring, even if the wiring is literally that simple. What do we want our signature here to be? Well, we want to set the focus, right? So we don't really care what it focuses because we're just going to set it to a B, no matter what. Well, we can see this takes a function from A to B. We can construct this by literally saying, okay, set of some setter. We can run over where it's const of, so this will be the B, const of the value, over setter. So this will focus the focus, and then it will run this function, but the function really just always returns B. All right. So now we've got over, and we've got set, and we've got a setter. I wonder, are there other interesting setters that we might want to do? We could do one for like lists. So mapped, I think, is one in most lens libraries. So we could, in fact, I think, write this for any functor. So let's try that, actually. So let's say if we've got a functor f, then you give us a, then this will be a setter. So I'm going to switch this. Now that we've written it, we can see the setter. We'll write this out in long form. So first and second goes to first prime and second when we go from a first to a first prime. There we go. Okay, and mapped is going to, for some functor, it's going to take f of a's and it's going to turn them into f of b's by focusing the a's and turning them into b's. Okay. So how do we do this? Well, remember, setter, it takes a function, in this case, over the focus, so a to b. So this will be our function from a to b, or we can call it a to b. And it takes whatever the s is. So if a setter takes an s and goes to a t, well, then our s and t are going to be a container of a's and a container of b's is where it's going to end up. No, over is for readability. Over is, like you can, this is kind of what I was saying. So let's see, someone just mentioned in chat, do we really need over? No, we don't. So if we just take over out, so it was over the first focus, I wanted to not, and then I did, false Bob. I can just take out over, and it just runs fine. So this is an implementation detail that you can do this. For instance, this does not work with Van Laerhoven optics. Van Laerhoven optics default to being a traversal, and you can do traversally things. But it's really just a quirk. I would say this is not very readable, so I recommend using it, or you can use the infix, which we haven't defined yet, but we can do that right away. Yeah. So this will be our container of a's. So this can be a list. This can be a dictionary, a map, even a function, whatever you want. And we need to somehow run it. So in this case, right, it's going to be fmap. We're going to fmap a to b over f of a. And strangely, by actually running this fmap, we've constructed a setter. So a setter is just anything that knows how to find some focus within some structure and edit it. Setters do not necessarily know how to access, right? So, you can write a setter, this mapped setter, this will work on I/O. Even if you can't pull the value out, you can still run a setter on it. So, let's try that out, actually. So, what's an I/O value? So I can do like getLine, I think. Yeah, so getLine should be an I/O of a string. Yep. So what if I want to run a setter on getLine? Here, let's do it over here. So so now I can say over mapped, I want to, let's uppercase them. So for that, I'm going to do import data dot, or actually, no, let's do reverse. So I'm changing my mind a bunch. Sorry about that. So over mapped, so we're going to map over the I/O, then we're going to run reverse on getLine. Now, because I'm in GHCI, it is going to just run this I/O action. So we'll see this. You can see it still is an I/O of string. And so if I actually just hit enter here, it's going to run it. It's going to wait for me to enter my line of input. And when I hit enter, well, it ran the I/O action and then mapped reverse over the output and then printed that out because I'm in GHCI. So that's kind of cool. So setters are extremely easy to implement. You just really need to be able to find something in a structure and change it. Okay. So we'll notice something interesting here. And that's that these actions, right? So actions, they take concrete profunctors. So in order to actually use $, I need to know that the profunctor used in the optic is a function, because I can only apply functions, right? But we're gonna get more general. So we actually don't need this profunctor here. I'm just gonna get rid of that. Let's write slightly. Let's write view now, or let's write a getter. So I'm gonna rename this library here to, instead of lib, this will be our setter.hs, and we're gonna just change the module here. Questions on setters before we move on? Gonna add a getter.hs. I realize I have not explained this terribly well. We'll come back to it once we've looked at some other ones so that we have something to kind of compare it to. That's I think the tricky bit is we have no way to compare. This is also it's kind of tough to explain this on the fly, but we'll do our best. Okay, so now I've got getter, so I'm going to make module getter. Now, what is a getter? Well, let's start by writing our action. So view is the canonical getter action, and we take a getter, STAB. Now, in the case of getters, because we don't actually edit anything and we don't return anything, we only return the focus. We really only need 2 of these parameters. You'll see we actually do need an extra one here. It gets kind of weird, but we'll see how that works in a second. So if we want to view, we take the getter, which can be a lens or whatever, or it can even just be a getter function, and we want to, given a structure, pull the focus out. Okay, so that's pretty simple. Now, how do we implement this? Well, if we remember that optics basically go PAB to PST, we have a problem, because this optic, while, you know, I can run this optic on some profunctor that accesses, you know, an A. So let's say I put ID in for this P, then I can force B to be, you know, A to A or something. But then it's just going to change it into this other form, and I lose my handle on the A. How am I going to get an A out of this sort of structure, right? It seems kind of impossible, for lack of a better term. Well, it is not impossible. We will see how it is possible. We get to choose what this getter is. Now, if we get to choose what the getter is, let's define our type getter. SA, we're going to change that soon. We know that it needs to kind of match something like this form, but we get to choose what P is, right? Because P can have any requirements on it that we want, any constraints. And that also includes, we can pick a concrete P. We can choose a profunctor. So for setter, we chose to use the arrow profunctor. Okay, and that allowed us to apply it, right? So by choosing that this profunctor must be the arrow, it allowed us to just use the $, apply it, and do some magic. Here, we need to keep track of the P so that we can get it out after our optic has been run. So we're going to define a data type, which is a profunctor. And it is something called forget. I'm going to call this R, S, and A and B, I think. It's been a long time since I've done this. We're going to try and get it right on the first try, but good chance I will not. So I believe forget just does, is it A? What's going on here? We've got this phantom type B, okay? It doesn't exist. That's weird. But that's because we don't care about what this result is or what this result is. We only care about A, and we need to get it out somehow. Now, if we're going to kind of store it in the profunctor, that's why we had to add this additional type here. So the profunctor is when we have forget already partially applied. So we're actually storing information about the focus in the profunctor itself. Okay, so to do that, let's implement profunctor. So we're going to make an instance of, I'm going to write down my fake little profunctor instance here. We're going to just define everything from scratch. So profunctor dot hs, this is module profunctor. We had our class profunctor p where diemap. Did I still have this somewhere? No, I deleted it. Okay. So diemap has needs A prime to A and a B to B prime, and we go from a P, A, B to a P, A prime, B prime. All right. So now we've got our profunctor class back. So I'm just going to import that. All right. Cool. So now we can say our forget thing that we just made up is an instance of profunctor. Now, to get the kinds right, I do need it to be, we need to partially apply it so that we have two arguments, right? And we can see that our requirement here, that A be kind of like in the, A is in the negative position, right? We need an A in order to run this. And B, because it doesn't exist at all, it follows the interface that it must be covariant or in the positive position, because if it doesn't exist at all, it's kind of both in the negative and the positive position, and we can map over this and do whatever we want, right? So for instance, I can, if I want to, I can make an instance functor for forget RA, where fmap of f on a forget A to R. We can, like, we don't even need to run it, right? We can just repack this because there's no B, so like f mapping, we don't ever even need to do anything. This type checks and this is totally valid. So we're going to do the same thing here for a profunctor instance where we have diemap. I'm going to turn on instance signatures here because we're going to want it. Just put this right here. Okay. So diemap, in our case, I'm going to change these to be what we're kind of looking at here. So we need to be able to map over A to make it A prime. So we've got A tick to A, and we've got B to B prime, but we already saw before we actually don't need this because there's no way that we can apply it. And then we take this P. Now, because we're actually inside an instance, we can specialize P is forget R. And we can take a forget, and in here we've got this function A to R, okay? Seems weird. What are we going to use that for? That's bizarre. Now, what we do need to do, if you look at our types here, we need to change this A into an A prime, and we do have an A, so we can just pre-compose our A prime to A on the front of our existing A to R. And this, here, I'll close that. This does type check. So basically what this says is to diemap over a forget, well, forget only knows how to affect the input. It doesn't have any output, right? Or rather, the output is R, which is completely separate from the profunctor. And so because it's not part of the profunctor, like it's not one of the profunctor args, it will not actually be edited by anyone using the profunctor instance, right? Because this is what we would edit it with, and we're not even applying that. So, you know, it doesn't ever get mapped over. So what benefit does this give us now? Well, when we write view, I'm going to expand this getter into, let's say, we do the same thing we did with our setter, and we say we're always going to use forget as our profunctor. And I'm just going to add that extra type here. Now, this B and this S, they don't matter. They can be anything, right? We don't care. So I think I can quantify over them here and just say they can be, does this not work? Illegal, I need rank-in types in here. So this just says, I don't care what B and T are, right? We're not editing, we're not setting, we're not running over, we're just getting the A. So I do care about what the A is, but I don't care about anything else, okay? So how do we view this? So now that we've basically made the getter concrete, I can actually just expand it in our view function here. So the getter is the thing that does this. I'm just going to get rid of the for all there because it is implicit. Now we can start thinking, this is something that like we can actually work with, right? We know that we have this function that can change something. This is our optic. So this is the getter. And we have an S. So if I have a forget that handles R's, A to B, and I can change it into one that accepts an S. So remember the accepting parameter is here. So if I have one that takes in an A and does something with it, turns it into some R, and I have this magical function which can change it into one that takes the S, which is what I actually have here. How can I manipulate these to get an A out at the end of the day? Okay. Now, this gets a little weird, but what we can do is we can say, so my forget, is going to be this forget RAB. And in order to construct this, all right, so now we need an A to an R. Well, because we don't know what R is, that's impossible to write. But because R is part of the actual profunctor structure, we get to pick that, right? We get to pick any type for the profunctor that we want. And that includes R. So what can I do with an A? If I get an A, well, I want an A out at the end of the day. So what happens if I set R to be equal to A? Okay. Now we can say this operates over a forget of specifically A. And now we can see, after we've run the transformation, we still have a handle on this A somewhere. Okay. So what is a function that goes from A to R, where, you know, they're both A to A? We can just pass ID in there. Perfect. So this is crazy, right? What are we doing? Well, we have this function, this getter. So what happens if I run something that changes this into something like this? Well, we can see here, then we'll have one of these forgets. Now, we need to somehow run this on this S. So I am going to need to pattern match on this result. So we're going to unpack this forget, but now, instead of an A to R or whatever, now we have an S to A. This is where the magic happens. And we can run that S to A on S. Okay, so this is the actual working implementation for Vue. I'll show it off, and then we're going to go through it again, because I definitely feel like I rushed through all of this, and I don't feel like I've done a substantial job of explaining this. I apologize. If anyone has concrete questions, please ask them now. Otherwise, I will just go through the whole thing as well, but it'd be nice to answer some specific questions. I know this is huge information dump. We're going to back it up so that we can actually understand this. Then we're going to generalize so that we can have both a getter and a setter with a lens. Okay. So how do I view? So I'm going to load this up. Now we need to write some getters before we can actually use this thing. So what is a getter? Well, it's anything that can basically map over these forgets. So let's do the same getter here. Okay. So I'm gonna do the same thing and just expand this. Makes it a little bit easier to understand. Okay. So we know that we're getting a forget here. And we know from the type of forget that the function that's contained in there is going to take an A and return an R. So this is going to be A to R. And before we get any further, let's make sure that we're actually giving sensible names to these. So if this is the _1 getter, it's going to take in, again, I'm just going to do first and second. So we're working on tuples here. First and second. And again, technically this can be anything. It really doesn't matter. But this is kind of the sensible way of doing it. All right. So, perfect. This says if you hand me something that handles this first, I will return you something that, handles the second, or handles the full tuple structure. Okay. And we don't, I don't think, get to know what this R is here, but that's okay. We don't need to know. All we do need to know is that our output needs to be a forget, which must take in one of these and return an R, but the only way that we can get an R is using this A to R function here. That's the only thing that we have that returns an R, and R could be anything. So we must get our hands on an A. Sorry, this should be first to R. So the simplest thing we can do is we can say, well, if you give us a tuple that has a first and a second. I know I'm rebinding over those prelude names right now. Maybe I should not do that. I guess I could name them with ticks or something. That's probably even more confusing. Let's use A and B again. I'm sorry about that. Great. So we get past this tuple of A and B, and we have this A to R function. Then we can just, of course, run it on the A. Oh boy. Okay. So chaos and anarchy, right? What actually happened here? So blah. Let's try it out. What happens if we view the first of our tuple and we, again, just pass it false and Bob? We should get false out, right? And we do. Great. So that seems to be working. Now we have the fun part. How do we, okay, yeah, let's go through view again. Let's go through view. So what is forget? Forget is something that accepts an argument. So remember, all profunctors have kind of input and they have output. So forget is going to accept its input, but never route it through the output. Yeah, the B in the definition of forget. Yeah, that's tricky. So forget accepts an A as an argument, as input. That's kind of the intuition. And it will never output anything. It'll just kind of be a dead pipe, right? It's not ever going to give you a B. The B will never exist. The B is, for all intents and purposes, void. It will never exist. It does not exist. It cannot exist. Okay? And because we know that it will never and can never exist, anywhere that we use this B, we can use it as whatever we want. We can map over it. We can do all of these things, because Haskell will never run that code. It doesn't care. The type doesn't exist, and so we can treat it as though it were anything. We can cast it into things, all of that. So why is that handy? Well, it comes in handy because of this R. So what we're doing is we're effectively redirecting the pipe from this general form. So if we always have a PAB, where we're not allowed to, we always have to map over the A and the B, and we have this PST here. This is what an object looks like. We know that this B is going to get forgotten. It's going to get re-embedded in the structure, and we won't be able to get a handle on it. So what we do instead is we redirect the A from the output into, forget can be a new type, that's true. We redirect the A from going to the output. Instead, we're stashing some transformation over that value inside this forget data type, okay? And then we can save it for later and access it later. So then when we basically implement, this is actually not important, we don't need the functor there. When we implement the profunctor instance, really all we're doing is saying we are allowed to tack some transformation in on the input, right? We can alter the input to this pipeline, and we can feed input to this pipeline, but over the output, well, you can do whatever you want to the output. It'll never actually happen, right? We don't run that function. The output disappears. The output will never actually output anything. Now that does mean that, we can't use forget with setters because there's no output, but the type system will prevent us from doing that, luckily. So forget is a profunctor which implements different profunctor classes than function, for instance. So function, we'll dig into the profunctor classes now that we have to get to lens and see how that works. So how does this work? Well, what we're doing basically is rather than manually implementing this in terms of forget, right, we can do this using our profunctor instance, I believe. So if we know that this is a profunctor, whoops, I'm forgetting how to write Haskell again. There we go. Okay. Great. So we can generalize this to profunctor now, and all this is saying is we need to be able to take something that maps over A and A prime and turn it into something which works over this structure. Well, we can use dymap for that. So dymap takes a profunctor, and we need to pass two things. So let's use some type holes here. And you can see it is happy, it is compiling. We just need to fill in these two holes. So the first hole, we need to, get the first element of the tuple. This is really easy, right? This exists, we can just use first. And the second one, we need to embed this into this structure, but the fact is, we know that for forget, this will never be run, right? This can't ever be run, it simply won't. So what we need to do is we need to be a little bit more specific than just profunctor, and that's why we just embedded forget. But there is a different way to implement this using something other than dymap, which allows us to both do the setting and do the getting without knowing what P actually is, okay? So profunctor is not powerful enough, right? Because we cannot actually write this function. We can't pull a B out of nowhere, right? In this case, if we were to just put undefined in here, which you shouldn't ever do, this would compile if I turn on tuple sections. It does compile, but obviously if I try and set, or if I try and use this as a setter, it's just gonna break because this is invalid. This is no good. So Now, for the hard part, how do we turn this into a lens? Okay. Well, lenses need to be able to view and set, meaning anything that we implement using a lens. Actually, here, let's do. All right, so we'll make a lens here. Module lens, where? Okay. It's going to import my weird profunctor class. Whatever type we give, I'm going to make rank in types for a lens. We're going to have some p, and it's going to do this, just like before. But we need some constraints on it that will let us both, do kind of setting and getting. Now, I don't actually know how people derived what these classes are and how they work, other than basically trial and error. You can stare at the stuff and think about it for a really long time, and you can get places. But what actually does go here is choice. So, or sorry, not choice, strong. It's strong for lenses. So strong is a profunctor class. So let's see if we have it in here somewhere. There we go. The output, or both. But strong, we can also run these two functions down here. So we can say, okay, first allows us, if you give me a profunctor, any profunctor that implements strong, and that takes A's as input and B's as output, I can change it into a profunctor, or like a pipeline, basically. We can think in terms of pipelines, which take both an A and a C. It runs the pipeline over the A's so that we get the output from the pipeline, but it leaves the C's untouched, right? So it basically allows us to feed something through the pipeline without altering it, okay? While also running the pipeline on the first part, okay? So this basically just allows us to like package up some stuff with the input and say, hey, don't touch this part. And we can either, ignore the first bit or the second bit of a tuple, okay? So I'm just going to copy paste this and we're going to implement it. There we go. And I'm going to make a new file here. Well, let's just put it all in our profunctor file here. So now we have a class strong p, and all strong profunctors must be profunctors. And we end up with these two methods. So you actually only need to implement one of them because we can kind of recreate the other in terms of just rearranging the tuple, the input tuple. So in Haskell, we represent tuples this way. Great. And if I really wanted to, I could, for instance, actually write out the default definitions of these, right? So if I want to implement first in terms of second, we can do that, but I'm not going to bother. Really, we only need one of these, so I'll leave that as an exercise for the reader. We'll just keep first for now. Okay. Now that we've defined this class, where we say, okay, we can, accept input and pipeline through some other stuff, can we say that this this setter here, can we define this setter in terms of only this type class? Because if we can do this action in terms of only the power that this gives us, then that means we can use this with any concrete profunctor that implements strong, which means we can use the same optic for setting and getting if both the arrow, which we're using for setters, implements strong, and for get, which we use for getters, implements strong. Okay, so we have basically two sets of things. We have data types like forget and functions, and we have, so these are profunctors, and we have the profunctor classes like choice and profunctor, and there's strong, and there's, like traversing. There's a whole bunch of these. Well, we can kind of pair these up and say that any of these types can be used with any actions which are based on any of these classes, right? So that's kind of where we get this polynomial explosion of beautiful composability. It's through that pattern. So let's see if we can do it. So we still need to basically implement this pattern, but instead of saying that this is concretely a setter, Liam says, a useful way to think about various profunctor type classes as they relate to optics is that the arguments they receive are precisely the concrete optics. Useful way to think of the arguments they, yeah. Yeah. Okay, so we want to generalize this from being a setter into being only dependent on the minimum amount of power that we could possibly want. So in our case, I know ahead of time that this is strong. There are ways to figure that out. They're kind of out of scope for us right now. So it's going to be an optic, which means, I should really define an optic type alias here somewhere. Type of an optic is exactly what we've been saying it is. Whoops. Takes something that operates over the focus and allows it to operate over a larger structure. Great. That's all. So now we can import optic here. And we can say that this is an optic, and we've added this additional strong constraint. And we can see actually up here, that's exactly what we've got. So we can say that this is a lens. Okay, and we can fill in S and T here, just like we've done before. And this goes to A prime. All right. So it focuses the first element of a tuple, allows us to change it from A to A prime if we want, and then returns this larger structure-ish. Okay, so how do we do this using only this method from strong? So I'll pull that method up here. Where did I put it? Profunctor, strong. So this is all that we have to work with. And of course, dymap, because we know that every strong profunctor also has dymap. Okay. So this gets kind of fun. So we have some P, we know that. This is the P, A, B. That's what's coming in. We know that because if we expand the type of lens again, right, it's P, P of here to P of, all right. So we've got this coming in, so I guess this is technically, P, A prime. I usually just call it P. And we need to somehow turn it into a P that operates over these, right? Now, in this case, this is pretty trivial, I guess, because we've got this function here, right? So if it says, if you give me a pipeline that operates over something, I can make it so that it'll pass through the other side untouched. And that's exactly what we've got here, right? We need to pass through this B untouched. And we need to operate on the A. So this will just seem kind of like magic, right? So, I can run first P, or we can, of course, say that, in this case, this is literally just first, right? We're just saying, oh, only run the pipeline on the first part of the tuple. And that's great, it's done. Now, problem is, we've got this defined, but we can't actually run, let's say, like view. View we've defined in terms of forget, and if I try to run it, so if I now do, here, let's hide these because we don't want them around anymore. Where's my setter version? Get rid of that. All right, so let's import our lens here, and let's import our getter, and oh, no module getter. It's annoying when it does that. I'll just import them here. Setter is not loaded. What are you talking about? Oh, saw lib. Got to change this. All right. Good. So if I try and view this thing, it's not going to work, right? Because it's saying, oh, okay, I don't have an instance of strong for forget, right? So the forget comes from view, and the strong comes from this first lens. So let's see, maybe we can actually define this class on forget, right? So where did I actually add forget here? So normally this should be in its own library. What I'm going to do is I'm going to pull it out here and put it in its own module here. Actually, you know what? Let's put all the profunctor stuff together. Otherwise, we're going to confuse ourselves. So I'm going to define forget in this file, and now we're going to see if we can make an instance of this weird strong thing for forget. And remember, we always have this kind of extra magic parameter hanging out for forget. That's where we get our benefits from. Cool. So how do we do this? So we need to implement, we're just going to say just first here, which has this type, and P is forget of R. This means we're not allowed to touch the R. It has to stay the same, because otherwise you're changing the type of our actual concrete profunctor, which we're not allowed to do. But what we can do is we can pattern match on it, and we can kind of mess with it, right? So in here, looking at our new type, we know that we've got this A to R. So this is A to R. And we need to, well, this is what I usually do. Honestly, I know I need to forget on the way out. And I've got an A to R. What do I need to do to it, right? So I'll just put in a type hole and say, okay, I need to do something to this A to R. Which function can I run on A to R to make this all work out? And it says, okay, you need to take in that A to R and adjust it so that it takes a tuple with the C in there to R. Well, looking at this, since I'm working with a function and I need to change the input, I'm going to rearrange this type hole so that I'm pre-composing it, right? So now I run this function first and then I pass the result in. And we can see here, now this function is just A comma C to A. And that's just getting the first thing of the tuple. So I can just say first there, right? Cool. So we've implemented first, right? And it just says, okay, well, forget really just transforms your input into something, and we don't need to worry about the output. So of course, when we implement first, how do you run a pipeline on, you know, just the first part of a tuple? Well, you can just get the first part of the tuple and then fire it through whatever else you were going to do. And we don't need to worry about the output because forget does not have output. All right. But we need to do, so now we should be able to view, I believe. Right. So we can view. So how is this actually working, right? Like, it doesn't seem like we actually wired everything up properly, but by saying that this is how you do things on the first part of a tuple with forget, and by saying, well, to do the first part of a tuple, we just use first, the profunctor knows how to just implement this for forget now. And so when we apply it using view, currently this is still hard-coded to forget, but that's fine. And it will run this transformation, focus the first part, and away we go. So that's kind of cool. But we still need an instance of strong for our arrow type. Now, all of these instances, of course, you can just import data.profunctor. I'm writing them out from scratch so that we can kind of see how it all works, right? But in reality, you do not need to do this. And the ones that are implemented there are probably more performant anyway. But I'm hoping the types prevent me from making mistakes. So, okay. So, no instance for profunctor. Well, of course, there is an instance for real profunctor, but because we're defining our own profunctor here, we'll have to implement that ourselves. But that's okay, because it's really easy. So instance of profunctor for functions, where it's really quite easy. So if we need to run a function on the front and on the back, well, we can of, I guess, some function h. So I guess this is what? Before, let's just call it before. And after on some function, we just say, well, we just compose them all in the right order. And it's happy. So do this on your input, run the pipeline, do this on your output. Now we have a profunctor. Okay, now we need to make it strong. So just like before, oops, this is kind of fun. So we've replaced our p with, instead of forget, now our p is this arrow, right? And I'm just going to group these up for clarity here. Okay, so we need to take a function which operates on the first bit of a tuple, and then, function that operates on, just an a to a b. And we need to lift it to operate over this tuple, right? Well, this function, it does already exist. It's in, I think it's in control.arrow. But ironically, it's called first there as well. Yeah, so ambiguous type first. So if I do control.arrow.first, what's the type of that? We can see that it does exist, and it does exactly what we need it to. But rather than import that, I'm just going to implement it again, because it's quite easy to do. So if we've got an A and a C, and we've got this F, we can just run the F on the first chunk and leave the other half alone. Done. All right. Cool. Thanks for sticking with me. Okay, so now we've defined strong. So we should, in theory, if we still have this implemented in terms of strong. So now we should be able to set. So all of our setters should work now. So if I try and set the first part of this tuple to, I don't know, 42? No, it's a problem here. Set, I need to, I think, provide this first, 42. Maybe I need some more types here. Found whole, where it's an ambiguous type variable. Yeah, okay. What am I doing wrong? Found whole. Oh, it thinks it's a whole because I have not imported it. That's all. So I just need to import lens here again, and it should work. There we go. Okay. Do I even need this? I don't think I need this. I'll probably just default. Good. All right. So we have built lenses. We built a lens, and it's a really, really silly lens. So the last challenge we're going to do here, I think, on this stream is I'm going to try and get some coffee here. Last thing we'll do for today is we're going to implement the generic lens helper function, which will allow anyone to build a lens without thinking too hard. So this one's really common if you look inside the lens library. Most people use this all the time. Basically, it says if you can project from a structure to the focus, And you can basically say how to, if you give me something, I can set it in that structure and end up with some result. Then I can build for you this lens. So we're going to build this helper. I'm copy pasting directly from the lens library, but it's fine because it's the same in the profunctor. Exact same signature in the profunctor world. It's just the type behind this lens is going to be different, but that's okay. We got a question, sorry. Can't set false to 42. Oh, okay, so we had a question in the chat. We can't set false to 42. They've already clarified, but this looks weird, right? Because false is a Boolean and 42 is some sort of numeric type, right? So why can we even do this? Well, this is, again, it has forgotten my imports. I really gotta fix that. Okay, try again. There we go. So the reason we can do this is because this thing, you can see that the input structure has one type in the front, and actually the output, this A prime, is a completely different type. It might be related to the A, it might not. Maybe I should use a completely different type variable name here, but in theory we can change the type to be anything that we want. And this is kind of one of the benefits that optics give over just traditional traversals, is that they can, change the entire structure type, not just the kind of type parameter. We can pick anywhere we want in the structure and change the type. So that's how that works. Okay, so let's write this thing. This is going to be the hard part, but we're gonna. I believe we can do it. So we've got our getter. That's what this does. Gets our focus. We've got our setter. This takes the existing thing and the new focus and will adapt it. And we don't need to know how that's implemented. Whoever is going to be creating a lens using this helper is going to do that for us. And then we need to end up with this thing. Now, what this is this is going to be this function here, which is going to expand into, again, PAB to PST, okay? So that's the end result. So we can actually bind this PAB here. So this is the input profunctor, and this goes from P, it's a profunctor from A to B. So it takes A's inputs and it returns B's. And we need to, in this slot, this will hopefully tell me, I need to create a P that takes S as input and returns T as output, okay? Oh boy, so this is where you start to get into a type Tetris, right? So there is, I believe, exactly one right way to do this, and you just have to fiddle around until you can find it. So there's really like no, there are probably better and worse ways, but if you can get it to work, it'll probably do the right thing. And that's the beautiful thing about these profunctors, right? Is they're so generic that if you can figure out how to do it, it's probably right. It's probably going to be right. So what can we even do? So there's two things we need to do. We need to change this, the input of the profunctor, so that instead of accepting A's, it accepts S's. And the other thing we need to do is change the output so that instead of outputting B's, it outputs T's, okay? So the input is probably the easier one to do. So to change the input, we can basically run this getter over the left half, the input part of our pipeline. So I'm going to use DieMap. Normally I would use LMAP, but because of how we've implemented profunctor, I just actually didn't even define it. So I could define it. Here, let's define it. So LMAP has a default of DieMap F and ID, and RMAP leaves the left half the same and runs it on the right. We need types for these. All right. Cool. So one only affects the latter, and the other affects the former. There we go. And each of these have default implementations. So there we go. So now I can say I only want to map over the input, and I want to map over the input with the getter. I'm going to run that on PAB. And now we can see, okay, we're one step closer. What else do we need to do? So this is how I typically write them. I do one step that I can understand. Then we say, okay, what other steps do I need to do? So now you can see I've changed the first part of the S to a, the first part of an A to an S. Yeah, someone mentioned in chat, it's usually easier to work with the type holes if we don't even bind this P. I wanted to do it just for clarity reasons, because starting off point free can be very confusing for people who've never seen this before, right? But basically we're going to be creating a pipeline over this profunctor that changes it step by step from this into this. So it is of course valid to just delete this and do this point free, right? I usually when I'm teaching I'll just bind everything. But if you look in my Proton implementation, I definitely do it more so the pipeline-y way. Okay, so we're one step closer. Now, here's where we're going to get caught just a little bit. So we've got something that accepts as input an S and outputs a B, but we need to turn that into something which outputs a T. Okay, so how do we even get a T? T could be anything. So the only way that we know how to get one is by combining an S and a B using this setter. So if we can pass an S and a B to this setter, it will get us that T. But the problem we have is that the B exists on this half, right? Like the original output's a B. And the S is input. So how do we get the input into the output and then combine it with the B so that we can eventually end up with a T, right? That's it's a bit of a puzzler. Well, the only thing we have to work with is that we know this is strong, and we know that strong can basically, you can tell it to pass something through the pipeline unaffected, right? We can say, okay, operate your magic on the first part of a tuple, but leave the second part of the tuple alone. Okay, but we do want to still process this S so that we can get a B. Okay, so this is where it gets kind of fun. So here's where the type Tetris comes in. The first thing I'm going to do is I'm going to say, okay, well, I want to process that S so that I can get a B, but I need an S in the end to run this. So I'm going to copy that S. So I'm going to duplicate it. So over the input, I'm going to take an S and I'm going to copy it, basically. Okay. And I'm still going to need to do something else here. So what do we have now? So I've taken the S and I've put it into a tuple where it's just duplicated. It's on both sides of the tuple. And now it is very confused. So why is it so very confused? Oh, I think I need this the other way around. What does this do? Is it this way? Can I get it backwards? Conflicting definitions for S. Oh yeah, I'm doing something wrong here. Okay, 1 second. Maybe I need to do this before I run the getter. So I'm going to pull out some of these types. So what I need to do, I know that I can take a something is going to take a P of n something, and if I can get an S and a B on the other side, then I know I can turn it into a T. All right. Now, this can be anything, so I'm just going to call it x. We're just not even going to affect that. Okay. Now, this is easy to write because I know that if I want to map over this, well, I can use rmap, right? It'll run a function on that half. And I could use uncurry or whatever here, but I'm just going to pattern match. I'm going to say if you give me the s and the t, I can run the setter on it. On the s and the b. There we go. And I think I just need scope type variables here just to make all of this make sense. Now, where are we? What's the problem here? Cannot deduce profunctor p. Right, I need a p here as well. Or I can just quantify here. So for all p, if it's a profunctor, then we can do this. And the x, we can also say x can be anything. Okay. So I've got this something now. We're part of the way there. But I still need to carry that s all the way through. So we made it one step further, right? So now I need something that takes a p, s, and a b. So this is a pipeline that goes from s to b, and I need it to go from s to s and b, right? So when in doubt, DIMAP can usually help. You can kind of see what your holes look like, and you can see in this case, this one's just identity. It just takes an s to an s. So that tells us that we need to rmap here, right? Because we only actually do any sort of transformation over here. Well, no, I'm still doing something wrong. Okay, we need to use strong here, so I need to use first at some point. Can I just use first here? And then change it afterwards? Okay. Maybe? Ah, okay, we're very close. I was saying first, but really we want second. So I'm just going to, because we haven't implemented second, I'm just going to switch the ordering here, and it's going to be comma s. So we're going to run the pipeline to get the b in the first slot. We're going to leave s alone in the second slot. Now this will be a little bit more sensible. So we need something which can change from this profunctor into this profunctor. Now if we unify C0 with S, really all we need to do is change from S comma S into an S, and we can do that by duplicating, right? So now that we're affecting the first argument of a profunctor, we can use this lmap and say we're gonna edit the input, and here now we finally have this weird duplicate function. Okay, perfect, we made it. Okay, so we're gonna define dupe, and this is gonna take anything and duplicate it. Great. And we're going to duplicate the input. All right. Now this is often how this ends up. You just kind of keep hacking on it and keep hacking on it, and you don't really understand what you've done when you get it to the end, but I'll explain this with a little bit better intuition before we call it a day here. So let's also talk about what this thing is actually doing. Something is not a very great name. And basically all this is doing is it's saying, hey, we focus something from the input, and then we know how to combine it back with the structure that we had at the beginning. So this is passing the, here, let's try this in pipeline format here. So I'm gonna just unbind that. And now this is in kind of a pipelining style. It's in point free. So the profunctor is gonna come in on this side. First, what we're going to do is we're going to map the getter. So basically we're going to say, hey, we start off coming into this with a PAB, and this is something that knows how to operate over the focus. Now, we're going to say, I know how to get an A from an S. And so if we run that, if we kind of pre-compose that onto our pipeline, now we're saying, okay, if you give me an S, I'll get the A from it, and then I'll run the pipeline that you gave me, okay? So now we've got this, okay? Now, when we run first on it, we say, okay, I'm going to take this pipeline that goes from the structure into this edited focus, and I'm going to say, you're allowed to pass me something additional, and I'll just thread it through, okay? And this can be anything that you want. I'll just thread it through the pipeline unaffected. And what we want to thread through unaffected is actually the structure itself. So we're going to pull the focus out of the structure, edit it to get this B, but we're also going to keep the original structure there. Now, if we have the original structure and the edited focus, the setter knows how to combine these together, and so we call our setter, which takes the S and the B, and returns the T, and then we end up with something that takes both S's and returns the T. And then we're one short step away from saying, okay, well, I know how to go from one S into two, I'll just copy it. And that's our duplicate function. And so if we stick that on the front of the pipeline, then we say, okay, if you give me one S, I'll duplicate it, and then run the whole pipeline and end up with a T. So when we're writing profunctor optics, it's all going to be in this kind of pipeline-y style. And that's why it is quite confusing to work with. It's definitely not intuitive. But you do the hard work once, and you can reap the benefits later. Okay. Now, what's the actual intuition? So let's look at an example. So if I have, our canonical example here, false and Bob. If I want to, write this lens in this generic fashion, well, the getter is just going to be first. The setter is going to take a tuple of A and B and a new B. I guess maybe not tuple of A and B. I'm just going to call this the new thing. And it's going to put the new thing into the first slot. Okay. So what's the intuition? So when we do our whole pipeline, what we're going to do is we're going to focus this first bit with the getter. So we're going to pull false out. Okay. And then we are going to possibly run some function on it. So like maybe we run it through not, and then we end up with true. Okay. So this is going to correspond to the, however we're going to transform this. So we can get the first part of the tuple out. We can change it into the B using whatever means we choose. That's left generic. And then we need to know how to combine it back with the original structure, which is what this is doing. So we would then just re-embed it back in here. So it'd be like not false. Bob, that's left alone. That's not super intuitive either. Oof, this stuff's tough to explain. It's really tricky. I should really write up slides or something on how to do this. But yeah, I think we're going to probably call it there for today. If you have more questions, feel free to leave them in the chat. Sorry, yeah, this didn't go quite as smoothly as I was expecting. I'll have to do more prep work for the next one. But I'm moving next week, so I might not have time to do a stream for a little bit, depending on how the internet is in my new place and all of that, and when I can get internet hooked up. So this might be the last stream for a little bit. But yeah, so profunctor optics are very cool because we can express things extremely generically, right? So these profunctor classes are what give us the power, and there is just a polynomial explosion of classes and types and actions, and they all combine together to give us really, really cool properties. I'll show you something here. There's the canonical kind of pure script profunctor optics implementation, but don't need this right now. Okay. But there's also one in Haskell, so I kind of just experiment with profunctor optics in here. So I do have a full kind of optics implementation here. So you can come in here and take a look. So I've kind of split it up into profunctor classes. So I didn't re-implement all of the existing ones, but I have been experimenting with a few more interesting types in here. For instance, reflectors. So this is kind of like kaleidoscope optics. Which you probably won't find in any other library yet. And then I've also got, of course, the optics. So inside Proton here, I've got, we've got the getter, and we've got the lens, and we've got the setter, and you can come in here and see how all of this is implemented. So I'll just leave this as kind of the code examples. So they're quite similar. In certain cases, I have kind of been a little bit more generic, but you can see here, for instance, view is using an optic which accepts forget, and we're basically running the same thing that we did. So we use ID and we just run the forget. So these might be a little bit slightly tougher to read, but it's all there. And here we've got our lens implementation. So sometimes I like to go a little funky with the point-free stuff, probably not the most clear. And here's our setters. So here I am kind of manipulating the fact that you can run profunctors directly. And some of this stuff looks a little funny, but it is all in there. So you can feel free to check that out. That's Chris Penner /Proton on GitHub. And yeah, hope you enjoyed it. I do explain things with a little bit more lucidity and a little bit more clarity in my book because I actually had time to think about that and go through everything. So I do recommend that if you're interested in learning how to use optics. It covers basically what they do, how they work, everything that you can work with them. Feel free to read through the free sample and just see if it's something you'd be interested in. I have lots of examples. I have lots of code. You can see kind of what other people have thought about it. Yeah, check that out. It supports me and helps me keep doing things like this. And yeah, it's a lot clearer than trying to follow along on stream. So thanks. Have a great weekend, everybody. Catch you later.